Here we begin Unit 8. Unit 8 is all about the behavior of gases. This is going to involve a fair amount of theory and unfortunately a fair amount of math. All right, so to understand how gases behave, the first thing we need to discuss, is the kinetic molecular theory. This basically is a 5-point description of how gases generally behave. The very first one we're going to talk about is that the volume of gases, and again, this is not terribly surprising, is mostly empty. There's a much more snazzy way of saying that, but this is basically what this point says. The formal way to say it is that the distance between the gas molecules is greater than the size of the gas molecules themselves. Well, duh, it's a gas. But basically what that says in regular English is that the volume of a gas, however large it is mostly empty. Again, this is not terribly surprising. The next thing is that their collisions are what we call elastic. An elastic collision is basically where no kinetic energy is lost. So if you think of like a really bad head-on collision of two cars traveling down a road, when they slam into each other, that would be an inelastic collision because both of them are going to lose their kinetic energy. They're both going to come to a complete stop, and there's going to be a massive amount of wreckage. In a gas scenario, when two gas particles collide, they are elastic, meaning no kinetic energy is lost. They're going to bounce off, and they're going to continue going in a new direction, but with the exact same amount of velocity as, or speed, I should say, as they were before. They're not going to lose any speed whatsoever. They're going to bounce off. Think of like two really hard marbles, and you bounce them together, and they're just going to go off into a new direction, again, with no loss of speed. All right, the next one is that they are in constant random motion. The gas particles themselves, constant random motion. Okay, again, they are constant because gas molecules are always moving, and they're moving, quite quickly. And they're going in a random direction because, again, the direction they're traveling at any split second is dependent on what they collided with last, right? Just like on number 3, they're going to, or like number 2, they're going to bounce off, go in a new direction until they bounce into something else. So they're always in constant motion, and that motion is completely random. The next thing is there is no interactions between the molecule. What I mean by that is there is no attraction between them and there is no repulsion. So as they come closer, they're not going to go woo and go off another direction because they repel, or they're not going to go and kind of move towards something because they're attracted. They're just going to whiz right by each other. If they don't hit, they're not going to hit. So there is no interaction. Sorry about my R. That looks kind of funny. That's an R. Interactions. The last thing says the average kinetic energy depends on the temperature. Okay, so that's another weird way of saying something. Basically, as you guys probably already know, the speed of the molecules is dependent on the temperature. So if something is cold, the molecules in that substance are going to be traveling at a much slower speed. If it's a solid, they're going to be oscillating and kind of vibrating at a slower speed. If they're a liquid, they're going to be kind of flowing around slower. And if they're a gas, they're going to be flying through the air or the container in a much slower speed. Whereas if it's a hot gas, they're going to be traveling at much, much higher speeds. So their kinetic energy, speed, depends on the temperature. They go faster when they're hot and they go slower when they're cold. So that's what's called the kinetic molecular theory. And again, it describes basically how gases behave. Now, all that being said, what we need to talk about next is some of the properties of gases. So the properties of gases are as follows. We have expansion. So what that basically means is that gases will expand to fill any size container that they're given. So if we have a gas confined, say in a steel, those steel cylinders, gas cylinders, then if we allow it to escape, it will expand to fill an entire room. Again, this is not surprising. They are also fluids. Gases are fluids. You can actually have, and I need to share a video with you guys, you could have two gases at different densities, and you could pour one gas underneath the other gas if this gas is of a higher density. It's a really cool thing. You could do it if you have, like, say, some sort of visible gas like carbon dioxide as it sublimates from a solid to a liquid, say dry ice. You could pour something underneath that and it will actually elevate it. So it's very cool, but they behave like fluids. They flow and they move. They're very dynamic, not too different from a liquid, except of course a liquid is confined to the bottom based on gravity, whereas a gas is not confined by gravity as much. Of course, they're low density. Again, remember the number one of the kinetic molecular theory. Again, the distance between them is far greater than the size themselves. They are compressible. So this is how hydraulics work and other things like that, is that you are able to squeeze a gas into a very small space. And by squeezing a gas, you actually can use it to do work, because it's going to have a lot of force behind that. So they are compressible. Solids and liquids are not compressible. Diffusion, of course, as you guys know, diffusion just basically means that gases will flow from an area of high concentration to an area of low concentration. So that, again, not terribly surprising. So again, if someone's like you're driving by a restaurant, and sometimes you can smell that amazing food coming out of the restaurant. And again, that's the diffusion. The concentrations high of that smell is inside the restaurant, and as it's diffusing out of the building through the doors and the vents and so on. The next one is effusion. Effusion is basically where a gas can escape through a narrow hole. So again, think of that cylinder, those metal cylinders you see sometimes on the back of trucks. They use them for like welding and other purposes. If I was to open that valve at the top just a little bit, I'm going to make a very, very, very small hole, and that gas is going to escape with an insane amount of pressure. And that again is called effusion, the ability to escape through a very, very small hole. Think of, say, if I put, I had a beach ball and I poked a hole in it. It's not going to pop. Again, this is not a balloon. This is a beach ball. If I poke a hole in it, the air will escape through that hole. Okay, that's effusion. Now, all that being said, guys, what I'm describing as far as the kinetic molecular theory and these properties of gases, we describe as an ideal gas. These are, I want to say this. These basically follow the kinetic molecular theory, which is, I'm going to say KMT for short. That's the kinetic molecular theory. And this is used for research. So whenever we are in a lab and we're studying the behavior of gases, we're typically going to study what we call an ideal gas. That means all the conditions are perfect. They're following all the norms of what we expect a gas to do. Now, ironically, if we go out into the real world outside of our lab, the gases we're going to encounter on a daily basis are what we call real gases. And these do not necessarily follow the kinetic molecular theory. These are the gases that we experience on a daily basis, okay? So again, just to repeat, we like to study ideal gases because they follow the rules, and we could have norms, we could have sets, we could have things that are standardized across the planet, depending on the different labs studying the different properties of gases. But like I said, not all gases in the real world follow the ideal rules. Most of them are a little bit different. There may be slight interactions between the molecules, right? It doesn't mean they're not going to follow in any way. It's just that they're going to be maybe not follow it exactly to the T as far as our kinetic molecular theory, okay? Those are called real gases. Now, it says at what temperature and pressure, are real gases behaving more like ideal gases? So when does the real world gas actually behave like the ideal gas? And the way I learned this, and the easiest way to remember this, is kind of a silly little mnemonic, that gases are kind of like you guys in the summer. You have very low pressure and very high temperature. So again, it's the summertime, the temperature is very high. So I'm gonna go ahead and do this. High temperature, again, it's summertime, right? In the summertime, you guys have very low pressure. So that under those conditions, when the temperature is high, but the pressure is very low, molecules are moving very fast. They're not colliding, they're not confined very much. Remember the compressibility. Therefore, they're going to behave more like an ideal gas. Okay, I'm going to move on to the next point, really quick, and then I'm going to stop this video. I don't want to make it too long, but I do want to include this part here. All right, so what we have here, guys, is the relationships between pressure, temperature, and volume in the context of gases. Now, The way I've always taught this is we use popsicle sticks. So this is a yellow popsicle stick I got from one of our Spanish teachers. And if you notice, I have in the middle, I have the letter T, that's for temperature. And on the left side, I have pressure. And on the right side, I have V for volume. So you could do this either with a popsicle stick, or you could actually do it in your memory once I show you how to do it. But what you need to remember is that temperature must be in the center. And then pressure and volume could be on either side. It doesn't matter which side has pressure, which side has volume. They're just on the outside. But remember, temperature must be in the middle. Now, the way this works is, say if we are experimenting with a gas and we're going to keep our volume constant. So because volume is constant, notice I'm holding the side with the V. So volume is constant. So if I was to increase the pressure on a gas by raising up this popsicle stick, notice what the temperature did, right? As I increase the pressure, notice the temperature also goes up. So as pressure goes up, temperature goes up. If I decrease the temperature and I cool down the gas, notice what also happens to the pressure. The pressure went down too. So if I decrease, then the pressure will also decrease. So the way that we show this on a graph is that would be a direct relationship that's going to look something like this. Okay, so as temperature goes up, pressure goes up. As pressure goes up, temperature goes up, right? As temperature goes down, pressure goes down. They do the same thing. So that is a direct relationship. Now, this is called Gay-Lussac's law. It was a French gentleman. Sorry, I'm having to make sure I don't misspell it. So that's Gay. That's a hyphen right there. Sorry, guys. It's a dash. Gay-Lussac's law. Okay, so he basically said that these two properties, pressure and temperature, are directly related. They both go up. They both go down if the volume is constant. Okay. Now, if I was to hold the temperature constant and I hold the T on my popsicle stick, if I increase the volume, notice what happens to the pressure. The pressure decreases. If I increase the pressure, well, then the volume decreases, right? And of course, if I decrease that pressure, the volume will increase. So they're doing the exact opposite, much like a seesaw, right? So this is what we call an inverse relationship. So the way we show an inverse relationship on a graph is not a straight line, but it's kind of a swoop down like this, and that is called Boyle's law. Boyle's law is the relationship, the inverse relationship between pressure and volume if temperature is held constant. So you notice again, they're doing the exact opposite. All right, the last one is if I hold the pressure constant. Pressure is constant, so I'm holding that with my finger, and I'm going to increase the temperature. Again, you guys could already guess what's going to happen. Yes, the volume increased. If I decrease the temperature, the volume also decreases. So again, similar to Gay-Lussac's, these two relationships are direct, meaning they're going to do the same thing. So just like Gay-Lussac's, it's going to be a straight line, kind of like this, and this is called Charles' law. Okay, so those are the three laws you guys need to be familiar with and how they are related, how they relate pressure, temperature, and volume. Again, if you guys want to draw this on your note packet, that would be a good idea, just so you guys could remember. But all you need to know, again, to do this, whether you do it by memory or on paper, is the temperature has to be in the middle. That's all that matters. And then again, you just hold the variable that is constant and that is not changing, okay? All right, guys, that's the very beginning of Unit 8 and about the behavior of gases. Thanks again for watching.